Let's take a look at one last distribution using the goodness of fit test. This is going to be a Weibull distribution. Okay, we didn't talk, again, much about the Weibull distribution in class, though we did apply the method of maximum likelihood because it makes for an interesting example. So let's go ahead and go through the goodness of fit test for the Weibull distribution. So we have some failure time data. Again, failure time often follows a Weibull distribution, which is an exponential distribution is a special case of a Weibull distribution. And let's go through the motions. Okay, so what do we need to do? We need to find the min, the max, the range, the sample size, the number of bins, and then ultimately the bin width. Were we to create a histogram for these failure time observations. Okay, so what's the minimum value? Let's apply the min function here. So the minimum failure time observation, it was 1.3, and the maximum is 139.7. So the range would be the max minus the min. Okay, so the range is 138.4 time units here. In here, let's just count these. Hopefully we get 35, and we do. And let's calculate then the number of bins. Okay, so the number of bins is going to be the square root function, square root of sample size. Okay, 5.916. We would like to round up on that. So let's round up to no decimal places. So we get 6 bins. So the bin width is going to be the range divided by the number of bins. Okay, and let's round this up. Let's not go all the way up. It's close to 23. Let's not go all the way up to 24. Let's just round up to the highest decimal, first decimal, 10th place. So 23.1. How about that? Okay, so that should capture all of our observations. Okay, let's go over to the observed, the actual stuff that we saw. Okay, the actual minimum value was 1.3, and we're going to have 6 different bins here. Okay, so the first bin, the upper bound on the first bin is going to be the minimum plus the bin width. And since we're going to drag this down, we need to hold that bin width constant. Okay, so the upper bound on bin number 1 is 24.4, on number 2, 47.5, and so on up to bin 6. Okay, the upper bound on bin 6 is going to be 139.9, which captures our maximum value of 139.7. So that's good. So now let's find the number of observations that would fall in bin 1. Okay, so we're going to count if. We're going to count in this range if the observation is greater than or equal to this value, 24.4. Okay. So what do we see? We see 26 observations in the first bin. 26 observations in the first bin. I'm sorry. Less than or equal to 24. It was a little scary for a second. 9 observations in the first bin. We want to make sure this is less than or equal to 24.4. Okay? And we want to do that same thing down here. But of course, what did we see? We see that this is everything that's less than 47.5, which includes everything that's less than 24.4. We don't want a cumulative histogram here. We want to subtract off everything in the previous bin. Okay? This is a brute force way to do this, but for pedagogical purposes, it makes a lot of sense. Okay? So now we've got everything in this bin minus everything that was before it, and we can just drag that on down. Okay? So we should get, when we sum this up, we should get 35. And we do not. So what are we seeing here? Ah, okay. Great. I would like to say I did this on purpose, so I'll say that I did this on purpose. whenever we drug this down, this cell down here and down to here and so on, what happened to the range that we're counting in? Okay, it keeps changing by one cell. Okay, that's what happens whenever you don't hold a cell constant when you should be. Okay, so we need to go back in and hold these constant. And then that changed everything that we did here. So let's go back in and subtract this off. Okay, and so on. So now we get a total of 35. Okay, so in bin 2 we have 10 observations. Up in bin 6 we have 4 observations. Okay, and the sum across all of those is all 35 observations that we should be seeing. So now let's go over to our expected observations. What would we expect to see in each one of these bins if the distribution is a Weibull distribution? Okay, let's go back and think about what our parameters were, beta and theta. Whenever we solve for this using the method of maximum likelihood, we found that beta was 1.39143, and we found that theta was 58.55128. Okay, so those were the optimal parameters that we found using the method of maximum likelihood, assuming that these 35 observations came from a Weibull distribution. Okay, so now we're actually going to determine, is that Weibull distribution and actually a good candidate for these data in the first place. Okay, so now let's do this like we did with the normal distribution. Let's find first the probability associated with bin 1. Okay, so we're going to implement this equation, this cumulative distribution function for the Weibull distribution. Okay, you can find this analytically using calculus. Okay, going back to the PDF, little f of t, that we saw in the previous one of the previous videos. Take the integral and find this, or I'm sure you can find this on the internet, and in fact Wikipedia will definitely give you the cumulative distribution function for most any probability distribution you want to read more about. Okay, so let's implement this. This is 1 minus exponent of minus t, so here's our value of t, divided by theta raised to the beta. Okay, and we want to make sure that this is all inside the negative. That's a pretty important consideration. And then we're going to close off the exponent. Okay, so what's the probability associated with bin 1? That's 0.2561. Okay, that's the probability that an observation of a Weibull distribution with these two parameters is less than 24.4. Okay, and we're going to drag this down, so we're going to need to hold beta and theta constant, but not h. We want this one to change. Okay, and so let's go ahead and do all of these probabilities. Okay, we don't want cumulative probabilities, of course, so what we want to do is subtract off for each one of these what was in the previous cell. Okay, and then in this last cell, if we just keep dragging this down, if we were to sum up these probabilities, we're going to get something close to, but a little less than 1. Okay, actually that's quite a bit off. So what we want here is, instead of finding the cumulative probability evaluated at 139 and subtracting off this probability, we want everything that's greater than 116.8. Okay, we want to go ahead and extend out to the upper tail, through the upper tail, all the way out to infinity. Okay, so to do that, we just want to say 1 minus that previous probability, that previous cumulative probability. Okay, so what this is saying is roughly 7.3% of observations lie above 116.8. Okay, note that's a little bit bigger than this one, and it's a little bit bigger because it's including all of those probabilities, probabilities of all realizations to positive infinity. We're not just stopping at 139.9, we're going all the way out to positive infinity. So those are really small likelihoods out there, but whenever you sum them all up, you get something that may be just a little bit bigger than that previous bin. Now, what would the expected value be? Well, we just have to multiply this probability by the number of observations, n. Okay, we're going to hold that n constant because we want to drag this down. Okay, so what is this saying here? This is saying in bin 1, we actually saw 9 observations that are less than or equal to 24.4. If it's actually a Weibull distribution whose parameters are beta and theta here, these optimal parameters using the method of maximum likelihood, we would expect to see 8.96. And for this next one, we saw 10, we would expect to see 9.46, and so on. Okay? We should, if we sum this up, we should get 35. And we do. Okay? So now let's compare the actual and the expected using our Pearson chi-square goodness of fit test. So how different is 9 from 8.96 squared divided by 8.96? And so on, across all k equals 6 bins. Our test statistic W is the sum of all those ratios. Okay, we have a pretty small test statistic. What is the p-value going to be for this test? Okay. We're going to use, again, the chi-square dist right tail. Okay, that's going to be an upper tail test. As always, this chi-square goodness of fit test, the Pearson chi-square goodness of fit test, always an upper tail test. We're always going to reject in the upper tail. That would tell us that this value is different from this value across k, because we're squaring this term. It's always going to get bigger. It's never going to be in the lower tail. Okay, so the value on the axis is this W value. Our degrees of freedom would be k minus the number of parameters minus 1. So here we have k equals 6 minus the number of parameters 2 minus 1. So we have 6 minus 2, which is 4, minus 1, 3 degrees of freedom. So our p-value here, 0.51923. Big p-value. Bigger than any alpha we would ever choose, 0.05, 0.1. Okay? There is no reason for us to reject the null hypothesis. And so what hypotheses are we testing? The null hypothesis is that the data follow a Weibull distribution. And we are going to stick with that hypothesis unless the evidence tells us otherwise. The data do not follow a Weibull distribution. Okay? So we do not reject the null hypothesis. We conclude that the data follow a Weibull distribution. Okay? Is that the very best distribution? Perhaps not. We don't really know for sure, but we do know that it's at least a candidate. Okay? It's at least a candidate. We have no reason to believe, we have no evidence that suggests that the data do not follow a Weibull distribution, but we can't say for sure that the Weibull is a best fit. Okay? We just at least know that it's reasonable for us to assume that these failure time data follow a Weibull distribution with these two parameters. Okay? There are ways to compare the results of different tests to determine which is a good fit and which is not. or which is the best fit, I should say. But let's not mess with that. Let's just say that let's not reject the null hypothesis and conclude that the data follow a Weibull distribution. Okay? And much like with the exponential distribution, a Bartlett's test was a little more sophisticated, a lot more sophisticated than the Pearson test. With the normal distribution, we saw there were a range of tests that were more sophisticated than the Pearson chi-square test, including the Kolmogorov-Smirnov, among others. For a Weibull distribution, the more sophisticated test is called a Mann's test. Okay? And that's a pretty complicated test statistic, certainly more complicated than this one, and it's been empirically shown to be a more powerful, a stronger test, especially when you have a Weibull distribution. Okay, don't use a Mann's test for anything other than a Weibull distribution, but it's especially good for a Weibull distribution, and better, technically, than the Pearson goodness of fit test. Of course, this Pearson goodness of fit test, why do we talk about this one? Well, it's because it's ubiquitous across any kind of distribution. Okay, it's a very general kind of test. We're just comparing the observed value from the expected value. How different are those two things? How different is the actual data that we have from the data that we would expect to see if our data follow a particular distribution? We're squaring that difference, so we've got an upper tail test, and we're normalizing, in a sense, we're scaling by the value of the expected value. Okay? And then we're summing those differences up across the number of bins that we're using. This could be applied to any kind of distribution, discrete or continuous. Okay? It may not be the very best one for each individual distribution, but it's good for all distributions. And that's why we discuss it. Okay? For pedagogical purposes, and of course, if you need something stronger, you now know enough about what a goodness of fit test is that you can go look up what the test statistic would be for a stronger test if you need it. Okay, so that's the Weibull distribution. Answering a set of hypotheses about a distribution given the parameters that we found using the method of maximum likelihood.